Hello everyone and welcome to today's webinar. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you would prefer to join over the telephone, just select Audio Options and leave Computer Audio and then dial into the telephone number displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation.
Thank you, Tracy. Hello, everyone. My name is Megan, and I will be the moderator for today's webinar. Today, we will be providing an introduction to modern hot isostatic pressing. This webinar will be a three-part series taking place today, March 1st and March 20th, so please save the dates. This webinar will run approximately 45 minutes long, and we will then open up for Q&A at the end. So today we will be talking about how hipping works, the main applications, and the benefits of hipping. Presenting today will be Dr. Johan Hjarne, Business Unit Director, and Magnus Ahlfors, Application Specialist. Dr. Hjarne, if you would like to start by telling us a little bit about yourself and what it is that you do for Quintus Technologies.
Hello everybody, I'm Johan Hjarne and I am the Business Unit Director for the Americas region, where I'm responsible for our hot and cold isostatic presses. I've been working for Quintus Technologies for 7 years and I relocated to our office in Columbus, Ohio last year. Before I joined Quintus, I worked in the aerospace industry for around 10 years.
And my name is Magnus Ahlfors. I'm an application specialist for hot and cold isostatic presses. I've been with Quintus for 5 years now, and I'm also based at our US site in Columbus, Ohio.
Thank you both. Quickly, I would like to inform the listeners that you will get access to all the materials presented in this webinar, as well as the recording shortly after the webinar is completed. So Dr. Hjarne, why don't we go ahead and begin with you?
Okay. Thank you, Megan. As presented here, this is the part one, the introduction to modern hot isostatic pressing. So if we go to the outline of the webinar, part one, I will start by introducing you all to our company, Quintus Technologies. Thereafter, Magnus will take over and talk a little bit about what hot isostatic pressing is. He will then talk about the benefits of HIP as well as the HIP cycle. I will then end up with talking about the equipment before I sum everything up. So, Quintus Technologies has its roots in Swedish ABB, which was among the first companies in the world to commercialize isostatic pressure technology. Our design principle for our hot and cold isostatic presses was developed already in the 1950s for the design and manufacturing of high-pressure presses producing synthetic diamonds. For these diamond presses, it is crucial to withhold extreme pressures, and for this purpose, our wire winding technology was developed, which we will talk about later on in the presentation. At Quintus Technologies, we are today around 200 employees. We have our headquarters in Västerås, Sweden. We also have a strong representation here in the Columbus, Ohio area, as well as in Shanghai, China. All in all, we have delivered around 1,800 high-pressure systems, and we have around 120 patents within our technology. In general, hot isostatic pressing is applied to achieve superior material properties, and if we look at the main industries for hipping, they are the aerospace industry, where typical parts that are being hipped are turbine blades, structures, or even discs. The automotive industry, where typical parts being hipped are casting from engine blocks or turbochargers. Within the energy sector, there are several industries that use HIP, such as the industrial gas turbine industry, where typically castings of the turbine vanes or vane segments are being hipped. In the oil and gas industry, as well as in the nuclear industry, powder technology is used to consolidate powder through near net shape for either a final part or for a billet. Medical implants is also an interesting sector for hot isostatic pressing, where typical parts are knee implants or shoulder implants and also hip implants. Something interesting to notice is that all of these sectors are very interesting for the fast-growing metal additive manufacturing sector, where hipping is detrimental to achieve the material properties needed, as will be presented throughout this whole webinar series. There are many ways to use hot isostatic pressing, of which three of the most common ones are densification of products. With this, you basically densify a casting or a 3D printed part, or a part that is produced from metal injected molding. So you have a finalized part which you refine with the HIP process by densifying products. Another way of using HIP is to consolidate powder, of PM HIP it is called, where powder is consolidated either in a canister to a solid piece of material, and this could be used both to create a material with very good properties, to be used for tools, for example, or you can actually design a part with near net shape. Diffusion bonding is the third way to use hipping, which creates seamless diffusion bonds of similar and or dissimilar materials with different melting temperatures. These series will focus only on the densification of products part. However, should you have any question regarding the other parts mentioned here on this slide, you are very welcome to contact us, and we will answer those questions as well. So now I give the word to Magnus, who will talk more about what hot isostatic pressing is.
Thank you, Johan. So I will focus more on the technical aspects here, and we will start pretty basic by explaining what is hot isostatic pressing, or HIP. The definition of the process is to apply a pressure distinctly higher than the yield strength of the material at the HIP temperature. So we have high pressure and high temperature, and at this elevated temperature, the yield strength of the material will be very low, and the stresses generated by the isostatic pressure that we apply will actually be higher than the yield strength. And we all know if we apply a stress higher than the yield strength to a material, it will plastically deform to, for example, close internal porosity. I have an example here below showing what hipping can do. So in the left picture here, we have two steel halves that has drilled holes in each end. And these ends were then put together and welded, and we created this slightly bigger cylinder with a big void inside. These specimens were then hipped, and we can see the results in the right picture. And these are cross sections, and the left specimen we can see here, that's a reference that has not been hipped. So we can see the big void here, or the big pore. And the specimen to the right here was an identical specimen, but it has been hipped and then cut up. And as we can see, this big pore is completely eliminated. One thing we can also see here is that we see some deformation of this hipped specimen, kind of to an hourglass shape here. And this is because this pore was so big, and then we can actually see macro porosity. But this is normally something we not see in the HIP process. The densification process during hipping is a combination of plastic deformation, creep, and diffusion. The plastic deformation happens quite early in the process. When we start to increase the temperature and pressure, the yield strength will decrease and the stresses in the material will increase. So you will start to collapse the internal porosity. The creep and diffusion part in the process is more time dependent, and that's why we have a soak time in the HIP cycle. And with the creep and diffusion in the process, we will not only be able to close the porosity, but we will be able to completely metallurgically heal the defects, so we won't see any trace of them after hipping. A short explanation about isostatic pressure. It is when the same pressure is acting on all component surfaces in all directions. So, for example, if you would dive down to the bottom of a pool when you're out swimming, that's the kind of pressure you will experience. In the case of hipping, we achieve this high isostatic pressure by a gas. I mentioned high temperature as well, and typically it's around 80% of the melting point of the material, with some variations, of course. Argon is the most common used pressure medium during hipping, and since we have this very high pressure during the hipping, we also get a very high density in the gas in the argon. And with this high density, we also get a very good thermal conductivity. And with a very good thermal conductivity, we get a very good heat transfer between the components being processed and the pressure medium. And this is good for the process. One thing to note with hipping is that it will only eliminate internal defects. So any surface connected porosity or any surface connected feature will not be eliminated by the hip process, since the pressure medium can penetrate these features. So a gas-tight surface is a requirement for your component to be hipped. I have an illustration here down below. We can see we have a couple of internal features here in the left picture, and with the hip process we can remove those completely. However, if we look at these surface connected features, here's a surface crack and just a rough surface or something, those kind of features will not be affected by the hip cycle. If we look closer on a surface crack, for example, it will not be closed by the hip process, but nor will it be opened by the hip process. This is a misconception that I hear sometimes, that people think that since we have a pressure penetrating the crack will open or enlarge during the hip process. But since we have the same pressure acting in the crack as all around the component, there will be no net force to either open the crack or to close the crack. The shrinkage in the process corresponds to the amount of densification we have. So for example, if we have a material with 2% porosity in the part and we hip it to 100% density, we will get the 2% shrinkage by volume. And if the porosity is homogeneously distributed in the material, the shrinkage will also be homogeneous all over the part. Here I want to show some real case example on the effect of hipping on densification. So here we can see micrographs of a metal casting. In this case, in metal casting, we normally see shrinkage porosity. And here we can see that the porosity ranges in size from around 50 microns to 300 microns. And as we can see in the picture to the right, we can completely eliminate this kind of porosity with the hip process. Another example is NIM material, or metal injection molding, and this material is very similar to the binder jet material in the AM industry in the as-sintered condition. And here we can see a lot of porosity, homogeneously distributed in the material, but they're very small, around a couple of microns big only. And as we can see in the right picture here, these porosity can be completely eliminated. However, we can see some black dots still remaining in the right picture here. And this is actually not porosity. In this type of material, we often find solid inclusions or solid particles, and they will also show up as black dots in the micrograph like this. So hipping will eliminate internal voids in the material, but it will not be able to eliminate any internal inclusion or particle unless the hip temperature is high enough to dissolve these inclusions or particles. A last example is for additive manufactured material, in this case an EBM printed material. And in the EBM process, we will get lack of fusion defects due to the printing process, or we can also have gas porosities originating from the powder itself. And as we can see to the right, this kind of porosity can also be eliminated by hip. And in the powder bed fusion processes, we normally get relatively high densities. It can be up to 99.5 or above percent density. However, we will always have some porosity in the part that can benefit from being removed by hipping. Now I will talk a little bit about the benefits of hipping and why is hip used. So as I've already mentioned, hipping is used to eliminate any type of internal defect in the material. And these defects in a material, they will act as stress concentration or crack initiation points, and this will negatively influence the mechanical properties of the material. And by removing these internal defects, we will be able to increase or improve the material properties. Especially for the fatigue properties, we often see an improvement of 10 to 100 times. We also get an increased ductility and fracture toughness. And since we're removing randomly distributed defects in the material, we normally see a reduced scattering in the properties. With that, we get more predictive material properties, and this allows us to use design values closer to the actual strength of the material, and that allows us to use low weight designs. Hipping will also give you better quality for machine and polished surfaces. I have an example here on the lower right where we can see a cast and machined part. So in the left picture here, it's a cast tube that it has been machined as cast. And as we can see, there's a lot of porosity that has been revealed in the machined surface. So this is probably an almost finished part that has to be scrapped because of this porosity, and that's of course expensive. On the right picture here, we have a cast tube which is then hipped and then it's machined. And as we can see, it looks like we have a perfect surface here. And this is very important when it comes to corrosion properties, optical properties for any kind of sealing application, and also actually for aesthetical properties. For example, hipping is actually used within the jewelry industry to be able to create these very nice surfaces that you have to have in the jewelry. Hipping can also be used in a purely economical sense. For example, in the casting industry, we can normally see, or we can often see, that casting are being rejected in the final non-destructive inspection because of too much porosity, or maybe we have porosity in the wrong areas, for example. And then that part has to be scrapped and remelted and recast, which is of course expensive. These parts can then instead be saved by hipping to save money. So you might not need the improved mechanical properties, but you can save money by saving a rejected casting. And I also want to point out one thing, is that strength is mainly determined by the microstructure and not the defects. So by running a hip cycle and eliminating the internal defects, you might not get a very big improvement in the strength. However, the microstructure of material is normally set by a heat treatment, and in a modern hip furnace, you can combine the hipping with all kinds of heat treatment. So in that sense, you actually can improve the strength with the hipping, but it will not be the densification part in the process that make a big contribution to the strength increase. Here I want to show some real case example of how the hipping affects mechanical properties. So we begin with the strength here, and this is values from a cast nickel-based superalloy. And we have cast material and hip material. And as we can see here, the maximum values of the strength doesn't really change by hipping. However, the minimum values of the strength is increased by hipping, and by that we also get a much improved scatter band, or a much reduced scatter band for this property. So we can see a reduction in scatter in 3 to 4 times. For the same material, cast nickel-based superalloys, we can see here the ductility in the as cast and hipped condition, and we can see that the ductility is increased with around 3 to 4 times. The typical effect on fatigue is here shown for EBM Type-64, and on top here we have the hipped curve, and this is a max stress versus cycles to failure graph. On top here we have the hip curve, and below we have the as printed curve. And just to show in comparison, I put some lines in here. So if we look at 600 megapascals as maximum stress, for the as-printed material, we get around 90,000 cycles. For the same stress with the HIP material, we get around 4 million cycles. So that's a big difference, more than 40 times better fatigue performance for the HIP material. If we look more into the details of the HIP cycle, here to the right, we can see an overview of a typical HIP cycle. And I will go into more details on these steps being shown to the left soon. First, I just want to say that the graphs we will see in this section will be log data from actual HIP cycles. And on the left vertical axis, we have temperature in Fahrenheit. On the right vertical axis, we have pressure in KSI. And in the horizontal axis, we have time in minutes. The curves we can see are in the graph. We have the black curve, which is the pressure, which is connected to the right vertical axis then. And then we have 3 different temperature curves. And these are from 3 different thermocouples in the furnace, in the hot zone of the furnace. And we have 1 thermocouple in the bottom of the furnace, 1 thermocouple in the middle, and 1 at the top. So a HIP cycle always starts with a vacuum and argon flushing cycle. And this is to remove the air in the vessel after opening and closing. And this is because we want to protect the furnace and the parts in the process from the oxygen and the nitrogen in the air or any other kind of reactive gas, so we don't get oxides or nitrites on the part or on the furnace. After the vacuum flushing cycle, we have a pumping and heating step. And this is where we increase the temperature with a predefined rate. And normally the pressure will follow so that the temperature and pressure reaches their respective hold times at the same hold temperatures or hold set points at the same time. However, it is also possible to control the temperature and pressure independently of each other. So in the example to the right here, this is kind of a stress relief cycle or step that has been incorporated into the HIP cycle. So here we start with a low constant pressure, but we're increasing the temperature to a predefined temperature, and we're holding there for some time, and then we're increasing the temperature again. And when the temperature has reached its set points, the pressure will be increased. I just want to mention here also that a stress relief can be incorporated in the HIP cycle, and normally you don't have to do it at low pressure. You can normally do it at the typical HIP pressures as well. But in this case, we wanted to do it at low pressure, and this is just an example to show kind of the flexibility of the system. When the temperature and pressure has reached their set points, the soak time will begin. And the soak time is normally between 1 to 4 hours long. And in this step, since we have so high density gas with this very high thermal conductivity, we also have a very good thermal accuracy. In this step, we normally see a plus minus 3.6 Fahrenheit accuracy, or even better than that. During the soak time, we can also change the temperature and pressure if we want. In this case, we have a different temperature for hipping, and then we have gone down a little bit in temperature, which was the typical solutionizing temperature for this material. So there's possibility to do changes during the soak time as well. After the soak time, we have the cooling step, where we cool down the system, the parts being processed and the furnace. And during the cooling step, it's normally desirable to have as high cooling rate as possible, because this saves time during the cycle, which gives you more productivity, so you can have a larger throughput of parts for a given size of HIP. And historically, the HIP units were naturally cooled, so you would turn off the furnace and let the system cool down by itself, and that could take quite a long time. In modern HIP systems, they are normally equipped with furnaces that has a forced convection cooling, which enables much higher cooling rates, so we can save a lot of time during the cooling. As we can see here on the graph, this is comparing an old HIP, so to say, with a modern HIP with rapid cooling. And as we can see, we can save a lot of hours for a HIP cycle just by the cooling rate. The high cooling rate in a modern hip system can also be used to run heat treatments or affect your microstructure, optimize your microstructure in the material. As we can see here on the right, this is for a nickel-based superalloy, and the slow cooling rate will give you a quite coarse microstructure, and then we also have a fast cooling rate that will give you a much finer and better microstructure. We will talk much more about this in the next seminar, which will focus on this high pressure heat treatment or combining hip and heat treatment in the hip. When the system has cooled down, we want to get rid of the pressure inside the vessel, and in our vessels we can actually reclaim the gas, and we can reclaim up to 95% of the process gas. So the gas you're using in cycle, we can actually reuse for the next cycle. So what we do is that we equalize the pressure in the vessel back to the gas storage, and when it's equalized, we actually also use the compressor in the system to pump back gas to the gas storage. This of course will decrease your operating cost for the hip cycle. When the reclamation is completed, the very remaining gas, the 5% of the remaining gas, will be dumped to atmosphere. And when this step is done, the system will be at atmospheric pressure and at low temperature. So then you can open the press and the cycle is completed. To finish off, I also want to present this graph. So this is pretty much to show the flexibility of a modern hip system. So this is a combined hip and hardening heat treatment cycle for a tool steel. And it's run as a conventional hip cycle and on the conventional hip heat treatment recipe combined. So we have in the beginning here a regular heating and pumping step, and then we have a regular soak time. However, in the end of the soak time, we increase the temperature somewhat to represent more the typical solutionizing temperature for this material. Then the material was quenched down to room temperature, and the quenching rate in this step was around 3,000 to 4,000 degrees Fahrenheit per minute. And then the cycle was finished off with a 3-time tempering step, where we've gone up and down in temperature 3 times, just according to the conventional heat treatment recipe. So this shows how great flexibility you have in a hip unit, where you can actually tailor-make your hip cycle and heat treatment cycle. Looking more into details on the hip cycle or the parameters of the hip cycle. As already mentioned, the hip temperature is normally around 80% of the melting point of the material. That is the solidus temperature. And of course, depending on material and application, this will vary some, but 80% is kind of the rule of thumb. The pressure is normally around 15,000 to 30,000 psi, and it will be somewhat dependent on the strength of the material. For example, ceramics, which normally have a very high strength, they are normally hit at maximum pressure. We have seen a trend within the hip community or hip industry that we're going towards higher pressure for metal processing. As also already mentioned, the soak time is normally between 1 to 4 hours, and most metals will have enough soak time at 2 hours. However, for the materials that are designed for high temperature creep resistance, they will need longer hold time, up to 4 hours soak time. And this is because, in the hip cycle, it is high temperature creep that we want to achieve, and these materials are very resistant to that. So it takes longer time to fully densify the material. One thing I also want to point out is that the main purpose of the hip cycle is to get to 100% density of your material. However, there will be different ways how to get there, or different parameter sets and different cycles can give 100% density. So which one of those parameter sets or cycles that you want to use, that's normally depend on other factors. For example, you might want to minimize the grain growth when hipping, and in that case, you probably want to have as low hip temperature as possible, and also as short soak time as possible, but still reach 100% density. So you might also want to increase the pressure as a compensation. You can also, for example, maybe you want to avoid or even permit the phase transformation to happen, so you would adjust your heat temperature according to that. Then I think it's you, Johan.
Okay, thank you, Magnus, for this part of the presentation. Now I will continue to talk a little bit more about the equipment and how we design our equipment with the wire winding technology. So as I mentioned already in the beginning of the presentation, Quintus has the wire winding technology, which was developed already in the 1950s as a way to withhold the high pressure. The pressure vessel is built from a thin-walled cylinder, as you can see in the pictures here, and is pre-stressed with a high-strength steel wire around the pressure vessel. The pre-stress of a cylinder from the high-strength steel wire creates compressive stresses on the inner surface of the pressure vessel, and then they remain throughout the whole heat cycle, which prevents growth from cracking. So throughout the whole heat cycle, there will always be compressive stresses on the inner surface, which prevents the cracks from growing. This design totally fulfills the ASME Boiler and Pressure Vessel Code, Section 8, Division 3, and is called the leak before burst design. As you can see on the picture to the left here, the thin-walled cylinder and the wire winding approach also gives the possibility to have cooling channels in direct connection to this thin-walled cylinder. So this gives this design the possibility to use the whole pressure vessel as a heat exchanger. So the hot gas can be within the furnace, and through a forced convection device, the hot gas can be forced towards the colder region and the cold wall, and then put back into the furnace again. And by doing this, we can create this very fast and rapid cooling possibilities that Magnus presented earlier. So this, of course, enables short cycle times, but it also eliminates or diminishes the need for safety-related inspection, because the pre-stress is in direct connection to the diameter change of the pressure vessel. So we can always, through measuring the diameter, validate and verify what the pre-stress in the pressure vessels are. So this is a very safe and also a solution which enables an unmatched performance. So, as understood from the earlier page, safety is something we take very seriously, and not only the mechanical design. When it comes to argon gas, all Quintus HIP systems are equipped with oxygen sensor around their systems. We also have pressure gauges and pressure relief valves to prevent the overpressures. All doors and protection covers are supervised. The designs fulfill the European Machine Directive as well the OSHA. But for safety reasons, we always recommend that operators are equipped with portable oxygen sensors when they are operating the HIP system. If we then come to the heart of the HIP system, which is the furnaces can be made from several different materials and different temperature ranges. I would say that the most common furnaces are molybdenum furnaces, which typically is used for metals, going up to temperatures somewhere between 2280 Fahrenheit to 2550 Fahrenheit, depending on what design you use. Other furnace materials would be graphite, for example, where you can reach temperatures as high as 3600 Fahrenheit, or stainless steel if you want to use lower temperatures. Typically, it's the material to be processed that decides what kind of furnace that should be used. Depending on sizes, the furnaces have different amount of heating zones to achieve as good temperature distribution throughout the full furnace volume as possible. Also, modern HIP systems uses TC feedback control, which gives a very good possibility to accurately control the temperature uniformity throughout both the full furnace volume and throughout the cycle. Accuracy that Quintus typically see in our system is that we have an accuracy of around plus minus 4 degrees F, or actually plus minus 3.6 degrees F, which corresponds to plus minus 2 degrees Celsius. All Quintus systems also have a rapid cooling capability, which we talked about in the earlier I should also say that due to that there is such a high pressure and a good temperature, the density of argon at high pressure and high temperature is very close to water, and this is why we have such good heat conduction rate between the gas and the component itself. So looking into the heat system sizes as such, all different kinds of sizes are offered, all the way from the R&D small production units up to very large scale production units. Looking at the smaller units, for Quintus, we have hot zone sizes up to 14.7 inch, and temperatures can go up to 3,632 Fahrenheit. That would be for the graphite furnace. We have cooling rates as high as up to 2,000 Fahrenheit a minute. So for these smaller units, we can definitely apply quenching directly into the heat cycle. All systems are designed to achieve pressures up to 30,000 psi. Looking at the mid-size production units, we're talking about hot zone sizes up to 41.3 inch. Here as well, the temperature goes up to 36, 32 Fahrenheit, which is a graphite furnace. The cooling rates for these ones are still very high, 390 Fahrenheit, up to 390 Fahrenheit per minute, which is good for cooling, for example, cobalt chrome materials fast and do the solution heat treatment step directly in the heat furnace. Again, the pressures these vessels are designed for pressures up to 30,000 psi. Going up to the bigger production units, up to hot zone sizes of 68.9. The temperature here are typically molybdenum furnace, a little bit lower, but still cooling rates which can go up to 100 Fahrenheit a minute. As you can see also here, we have pressures up to 30,000 psi. So these are the standard series, and of course there can be other sizes bigger than that, interesting as well. So to sum this up then, we started to talk a little bit about the company as such. Then we talked about the main industry segments that are using HIP: aerospace industry, medical implants, energy, and automotive, which all use HIP technology to achieve superior materials. Magnus presented the main benefits with HIPping, where you have superior material properties. You reduce the material property scatter, which means that you can actually trust the material properties better. And this is, of course, very interesting for the additive manufacturing industry. You can get an improved machine surface quality when you HIP, due to that you eliminate all subsurface porosity. You can also use HIP technology for scrap rate reductions. We also talked about the modern HIP systems and how flexible they can be in cycle parameters. You can use multi-processing, where you can apply both stress relieving, you can make changes during the soak time, and above all, you can do very fast cooling rates to increase the properties and the microstructure of the material. And as we just presented here, cooling rates up to 2,000 Fahrenheit in the smaller production systems are achievable. So, by ending this, I would just like to say that this was an introduction to HIP technology, and we have tried to answer as many questions that we typically get when we are out talking about HIP technology. So this is the basics. I would like to take the opportunity here to invite you to the coming webinars as well, which will talk even more about the high pressure heat treatment capabilities of our systems, where you can combine HIP and conventional heat treatment. The next webinar will be March 1st at 11 a.m. Eastern Time, and there will be a separate invitation for that. And the outline for that will be what high pressure heat treatment is all about, what kind of applications this can be used for. We will present what kind of research and development we are doing and how we are working with this. What benefits that comes out of this, what kind of equipment there is for this, and some practical examples of this as well. Finally, I would just like to say that we will, Quintus Technologies will be presented at Rapid, and we will have booth 509. And should you be at Rapid, please come by our booth and talk to us if you have any questions regarding HIP technology, or if you want to set up a meeting with us. We will be there with our whole team for that conference. And by that, I say thank you, and I leave the word to Megan.
Thank you, Johan. We are now going to begin answering the questions submitted during today's presentation. And as a reminder, you can still submit questions through the questions panel, which is located in your attendee control panel. So our first question is from Nigel. And Nigel says, is it possible to hit detailed or intricate parts manufactured via additive manufacturing rather than simpler or basic shapes?
And I can answer that. And yes, that is possible. I mean, the geometry you hit, it can be, it's no limitation on how complex geometry are. You can hit any kind of part with any kind of geometry. As long as the geometry will fit in the hip furnace, it can be hit.
Okay, so the next question is from John. Assuming the sizes listed are diameters, what height is available in those sizes?
I can take that question. I could say for the smaller sizes, the height would go up to, now I have to apologize because I talk SI units, but for the large, smaller system, there will be around 1 meter, a little bit higher. And going up to the bigger production systems, they can be up to 2.5 meters or 100 inches. So everywhere in between there, you can get whatever length you desire, basically.
Okay. The next question is from Ian. He's asking that you comment on porosity regrowth after hipping and then heat treatment.
Yeah, okay. And this topic will be covered in the third webinar, which will be a little bit more on an advanced level. So personally, I think that will be more interesting. But I can comment on it now. And if we print, there's a difference between electron beam melting and the SLM processes. So electron beam melting, you will have printing under vacuum. So any kind of lack of fusion defect will be under vacuum and they will completely densify. No, there won't be any regrowth. If you have gas porosity or you print in SLM, you have an SLM process. If you have argon in the pores will decrease in size and you will have high pressure argon inside of it. The argon will not diffuse into the metal. And if you do a post-heat treatment after that, you will soften the material, so the porosity could start to grow. And there are a few studies on this already, but it hasn't been addressed too much yet. What we've seen so far is that we have an initial size of a pore, we hip it to non-detectable limits, like below 2 microns or something in size. And then when you heat treat it afterwards, the pore can regrow a little bit, but it will not regrow to the initial size of the pore before hipping. And normally it's also a spheroidized pore, so it will that will benefit the fatigue performance. Also with our process, when we can hip and heat treat in the same cycle under pressure, you won't have this problem if by doing this pressureless heat treatment post-hipping. Also, of course, this is for argon. If you have a nitrogen gas atomized powder or printing under nitrogen atmosphere, that gas will actually diffuse into the metal so you can close all porosity. We will cover that more in the third webinar.
Okay. The next question is from Susanna. In case of 3D printed metallic parts, do you think that hipping is able to eliminate internal porosity in which argon gas is trapped, and also in the case of nitrogen gas?
Okay, so that was a little bit what I was talking about. And in the case of argon, you will not be able to diffuse the argon into the metal. You will decrease the pore size a lot, normally below detectable limits, but you will have a smaller high-pressure argon pore there. In the case of nitrogen, it will diffuse into the metal, at least for most common metals. So then you can close the porosity completely.
Okay. The next question is from Liang. How can the maximum density be achieved? Does it make sense for the AM part with 99.99% density by hipping?
So for hipping, it doesn't really matter what kind of starting density you have. If you have 80% or 90% or 95% or 99.9%. As long as you have a gas-tight surface, the hip, the part will be 100% after hipping. So if you have a 99.99% dense part, I mean, there's not much porosity in there at all that can be closed, but the very, very few pores that are in there would be closed.
And I can also comment, I mean, as you saw in the slide, you show that what we always see when we hit this part, the fatigue values will go up for after hipping.
Okay, thank you. The next question is from John. What is unique with a Quintus hip system in terms of safety?
Well, as you saw, we are using this wire winding technology, which is fully approved by the ASME boiler and pressure vessel code, as was reported. And I mean, these systems are designed to handle the pressures we are talking about. But not only is the pressure important, the gas is as important to think about. Argon gas is a gas that you need to know what you are doing when you are dealing with, and which is why we also always have the oxygen sensors equipped on our systems as such.
Okay, the next question is from Larry. Can you include post-processing like heat treatment into a Quintus hip?
Yes, we talked a little bit about that. We'll talk about that much more in the second webinar. But yes, you can, all kinds of heat treatments. And I mean, it's a very flexible system. We can heat, we can cool with different rates, we can have different hold steps, and we can add infinite many steps to the cycle. So yes, it's possible to perform most kinds of heat treatment in the hip. If you're looking at, for example, carburizing or nitriding or any type of that active atmosphere heat treatment, that we have done some research on, but we haven't developed it completely yet.
Okay. Our next question is from Benedict. What is the cost range of modern hip units you showed?
Well, we get a couple of questions regarding this, and what we always do when we talk about our hip system is that we evaluate for what they should be used. And please contact us, and we always do an evaluation of what kind of size of hip unit that is needed for the specific production, and then we will definitely come back with something that is suitable for you. That is the best answer I can give.
I mean, it varies so much from the size of the hip and the scope of it, so it's hard to say a number.
Yeah.
Okay, so that concludes the questions for the webinar today. I want to thank you, Johan, Magnus, and everyone else who has attended today's webinar for your attention as well as your participation. You will receive a follow-up email within 48 hours with a link to view a recording of today's webinar. And on behalf of Quintus Technologies, thank you for joining us and have a wonderful rest of your day.